Hello. So here we are trying to find out um, force on our charge Q3, and Q3 value is given in your problem as 30 nanocoulombs, right? So you have two positive charges, one negative charge, and you are given the distances between these charges. So this is 5 centimeter, this is 5 centimeter, this is 5 centimeter as well. The charges are given in nanocoulombs units. So 1 nanocoulomb is 1 times 10 to the minus 9 coulombs. So you're going to express all these three charges when you're calculating the forces in terms of coulombs, because that's the SI unit. We will also have to use meters for calculation of with involving any distances. Right now it's given in centimeters, so we'll have to solve using meters. So to begin with, the force formula for Coulomb's law is basically you have K, the constant, times the first charge times the second charge, and these modulus or modular signs are basically telling us that you will only take the positive number. You don't put any regard to the negative um, or the positive signs. It's over there. So irrespective of what sign you have your charges for, you're only going to use the magnitude of it and divide it by the distance between them. I'm calling the distance between two charges with index or indices that basically tells which two charges we're talking about. So if this is like between R, if it is between Q1 and Q2, then I'm going to talk about the distance between these two guys, which is this line. Okay. If it is between Q1 and Q3, I'm going to talk about these distance. Likewise, it is between Q2 and Q3. So since we are not interested to find forces between Q1 and Q2 in this problem, it's kind of irrelevant to write the formula in this way. So I'm going to edit my formula, or basically use the formula that's relevant here. Okay, so we are here trying to find out the two forces that are in between Q1 and Q3, and then Q2 and Q3. So I'm going to represent this problem in a slightly more convenient form, where I'm going to put them in X and Y coordinates, where I have basically these two guys, Q1, Q2, and then you have, let's say somewhere here, Q3. I'm talking about the origin here. Please disregard this small notch. So here we have 5 centimeter for each of these arms, so together this whole thing is 10. Not that we really need this, but I'm just still putting the numbers over there so that we can start working with them whenever needed. The first force that you want to know is between Q1 and Q3, right? And we know that Q1 is negative 50 nanocoulombs, right? And we know that Q3 is positive 30 nanocoulombs. So we will have to keep that in mind when we are trying to find out the directions. If you are just strategizing this problem, you will know that you have a positive charge here and you have a negative charge here. So your force is attractive and your force should be in this direction. Likewise, if you're trying to find out the force between Q2 and Q3, then your force should be in this direction. So this is if 2 on 3. This is if 1 on 3. Okay, so you have two forces like this. So our steps should be: first find basically if 1 on 3 magnitude, find if 2 on 3 magnitude, and then find if net using components, so that we can represent both the magnitude and direction of the net force. All right, so let's proceed. We are going to use the two versions of Coulomb's law, basically the same formula. So if 1 on 3 would look like K Q1 Q3 divided by R13 squared, right? We know everything else apart from R13. So R13 is square root of 5 over 100 square plus 5 over 100 square. This is basically 0.50, right? 25 plus 25, 50, and you have, no, I guess I'm making a mistake here. So let's make it correct. So it's 0.05 squared plus 0.05 squared, and I think it will become basically twice as much of 0.05 squared. So it's 0.05 times square root of 2, 0.05 times 1.414. Okay, so it's something like that. When you calculate this, it's gonna give you 0.07 in meters. Remember, we have to do everything in SI units. So we have converted the centimeters into meters. So once we know R13, we can similarly find out R23 as well. And that will also give us 0.07 meter. The reason being, you have, and how did we actually find this out, right? So we had a right angle triangle, right? This is 5 centimeter or 5 by 100 meter. This is 5 centimeter or 5 by 100 meter. So once we try to find out this length, that's the hypotenuse. So it's this square plus that square. Similarly, for the other side of the triangle or picture, basically, you still have the same base, same perpendicular to find out the hypotenuse. So either way, you will always have R13 and R23. Now that you know these two distances, we can find out force magnitude of R1 on 3, and that's 9 times 10 to the plus 9. That's the value of K, right? Yes, times 50 nanocoulombs times 30 nanocoulombs divided by R square, which is 0.07 squared. You calculate this and you'll get 2.7 times 10 to the minus 3 newtons. Similarly, if 2 on 3 will give you a very similar result, because you still have the same K value, you still have the one charge at 50 times 10 to the minus 9. You have the second one as 30 times 10 to the minus 3 because Q2 and Q1 are the same in magnitude, so it's not going to give you anything different. So now you have magnitudes for both and they are equal. Once we know the magnitudes, then we will have to work with the direction. Okay, remember this is how our forces looks like in our coordinate space. So let's just work with that. You have X, you have Y, you have one force that's going like this, you have another force that's going like this. We want to know the angle, right? You want to know the angle theta here, and you want to also know the angle theta here. Well, you can call them theta 1 and theta 2. You're going to see that they are similar. The reason being, if you are trying to find out this angle, you can start with this angle, and that angle, if you call this theta, then tan theta equals to perpendicular by base, right? Perpendicular is this, base is this. So perpendicular is 5 centimeter or 5 by 100 meter. Base is the same. This is 1. So theta equals to 45 degrees. Once you know theta, that's 45 degrees, you know that theta 1 is also 45 degrees because this whole angle is 90, right? Similarly, you can find out theta 2 to 45 degree as well, because this will still be 5 over 5. So we know that both these two vectors are aligned with an angle of 45 degrees. So if I now erase this, all this, so that we can use again our previous diagram, right? One force is like that, another force is like this. Let's maintain the color code. Oh, okay, so now we have to know the components, right? We know that now this is 45 degrees. That means if this is your F1 on 3, then you have y component as F1 on 3 times sine of 45, right? And then you also have an x component, this is our x-axis, component as F1 on 3 cosine 45. For the 2 on 3, this is F2 on 3. And let's make sure that you have the directions. Okay, so for 2 on 3, you have one component that is along the negative y-axis, right? This is F2 on 3 times sine 45 degrees. And then you still have one component along x, that is F2 on 3 cosine 45. So if I now want to list them, we have two components. One is the positive y, another is the negative y, and net y component will be f1 sine 45, sorry, f1 on 3 45 minus f2 on 3 sine 45, and 1 on 3 and 2 on 3 magnitudes are the same, right? We have just seen these are basically the same numbers. So if you are trying to just talk about the numbers here, they are equal. One of them has a negative sign, so they will basically give you 0 once you plug in the numbers. Net x component will be not 0, right? Because they are both pointing in the same direction. So you will have f1 with a negative sign because they're going, well, we can just do it in many different ways. f1 on 3 cosine 45 with a negative sign minus f2 on 3 cosine 45. So it's minus 2 times, basically because their magnitudes are the same, we're using the same magnitude here, right? 2.7 times 10 to the minus 3. So 2 times 2.7 times 10 to the minus 3 cosine 45 in the negative x direction. So your net force, in your example it's called F3, but it's going to the left. And if this is your x-axis, you can even express it in terms of I cap. You will say that this is F3 is 5.4 times 10 to the minus 3 times 1.414. I think it's 1.414. Let's double check. Cosine 45. Cosine 45. Sorry, it's 0.707. 0.707, and I will call it minus I cap or I hat, right? Because this is your positive direction. You're going to the left, so that's negative 1. So if I plug in that number, it will give me 3.818 newtons. Roughly speaking, 3.8 times 10 to the minus 3 newtons to the left with a negative I hat. You are welcome to use either unit vectors or just words, as your book says, right? Negative x direction. If you write it in words like this, should be fine in your solutions. So 3.8 times 10 to the minus 3 Newton, negative x direction. That way you would say your answer. Alright, so I'm going to stop here.